Imagine for a moment that you are a space explorer, soaring through the vast, silent darkness of the cosmos. You're on a mission, maybe looking for a new home for humanity, but then you see something strange. It's not a star, it's not a planet, but a patch of perfect, profound blackness against the backdrop of distant galaxies. This isn't just empty space, it's a black hole, one of the most powerful and mysterious objects in the entire universe. Despite its name, it's not really a hole at all. It's an incredible amount of stuff, an immense mass, crammed into an impossibly small area. We can thank the brilliant mind of Albert Einstein for the initial prediction. In his theory of general relativity, he showed us how gravity works. It's the bending of space and time by mass. A massive star, many times bigger than our own sun, spends its life in a constant battle. The outward push of its nuclear fusion, the inward pull of its own gravity. But when that star runs out of fuel, the battle is over. Gravity wins in a spectacular fashion. The star collapses in on itself, creating a supernova explosion, and if the remaining core is massive enough, it will continue to collapse into an infinitely dense point. This collapsed core is what forms a black hole. Think about our sun, which has a gravitational field 28 times stronger than Earth's. Now, imagine taking the mass of not one but 4 suns and squeezing all of that material into a space only 15 miles across, a distance you could easily drive in about 30 minutes. The gravitational pull of this object would be absolutely mind-boggling. It becomes so powerful, so intense that nothing, not even light, the fastest thing in the universe, can escape its grasp. This is why we can't see them directly. They are the ultimate cosmic traps, swallowing light and leaving only darkness. Every black hole is surrounded by a boundary, a line in the cosmic sand. This isn't a physical wall you could touch, but rather a theoretical border called the event horizon. It's the ultimate point of no return. Imagine you're in a boat on a river that is flowing gently at first. You can still paddle back to the shore, but the current picks up faster and faster. Eventually, you reach a point where the river moves faster than you can paddle. No matter how hard you try, you can't go back. The event horizon is like that for gravity and for the fabric of space-time. Once you cross it, your fate is sealed. The escape velocity needed becomes greater than the speed of light. Nothing can go faster than light, so escape is impossible. If you were just outside, you'd see a surreal sight. Stars, galaxies, twisted and warped, their light bent into a perfect circle of darkness. Back to our space adventure, your ship drifts closer and you feel the pull. Gravity accelerates you toward the event horizon. For an outside observer, something peculiar happens. They wouldn't see you cross. Your ship appears to slow down, it grows dimmer and redder, stretched by gravity. From their view, you're frozen in time, stuck at the edge. This comes from Einstein's relativity. Extreme gravity warps space and it warps time. To the outsider, time at the horizon seems to stop. To you, time feels normal. You sail across without noticing the exact moment. You're not frozen, you continue inward with no way to send a message back. Your two realities diverge. Now, if you're going to take this hypothetical plunge, the type of black hole you choose matters immensely. It's the difference between a swift, violent end and a slightly more prolonged, albeit still fatal journey. The most common types of black holes are called stellar mass black holes. These form from the collapse of a single massive star. They are relatively small, only a few miles across, but up to 20 times more massive than our sun. Their small size makes gravity change dramatically over short distances, and that is very bad news for you. If you fall feet first toward a stellar black hole, the pull on your feet is far stronger than on your head. That difference, a tidal force, would stretch you like a piece of spaghetti. This process is called spaghettification. You would be elongated, thinned, and torn apart atom by atom long before the event horizon. Your journey ends before it begins. So, avoid stellar mass black holes. They're not friendly to biological travelers. Aim for a supermassive black hole instead. These are cosmic giants with masses millions or even billions of times our sun. One such behemoth, Sagittarius A, sits at the Milky Way's center. Their event horizons are huge, so gravity changes across your body far more gradually. Tidal forces at the horizon would be gentle enough to cross unharmed. You've chosen wisely, you're falling toward Sagittarius A. Luckily, it's about 165 quadrillion miles away, so no threat to our solar system. Approaching the event horizon, your body stays intact. Gravity tugs on head and feet with almost the same strength, so you won't be stretched into a noodle. You cross the event horizon, the point of no return, without any immediate dramatic feeling. For a moment it might seem like you've made it. But crossing the threshold is just the beginning. The real challenge lies ahead, at the very center. As you pass the event horizon and venture deeper, your perception of reality and your friend's perspective from a safe distance become two completely different stories. For your friend, a frozen image, a reddish image eternally plastered on the edge of the black hole, they will never see you cross. They might watch for years, decades, centuries. From their frame, the light carrying your image is struggling against the immense gravity. Its waves stretch so far that you fade into an undetectable, low-energy signal. You have, in their reality, effectively vanished. But for you, the journey continues. Inside the event horizon, space and time swap roles. On Earth, we move freely in space, forward, backward, left, right, but we must move forward in time. Inside a black hole, this is reversed. The pull to the center makes forward in space the only direction. You can't turn around or escape. All paths, all possible futures, lead to the center of the black hole. This point is the singularity. It pushes physics to its limit. Theories say infinite density, mass crushed to zero volume. As you fall, tidal forces grow without bound. You be squeezed, stretched, atoms crushed out of existence until you're squashed into a point, becoming one with the black hole. Your personal experience, your thoughts, your consciousness, all cease at the singularity. You could never report back. You become part of the black hole's mass. This is the inescapable end. Friend sees you frozen. You have a finite, bizarre journey ending in obliteration. Two observers, two realities, one fateful fall. The universe has different rules depending on your viewpoint. For many years there was a big problem in physics called the information paradox. A fundamental rule of quantum mechanics is that information can never be truly destroyed. Information about an object, like its atomic structure, is always preserved in some form. But if you fall into a black hole and are crushed at the singularity, what happens to the information that made you, well, you? It seemed to be lost forever, a violation of a core principle of physics. This puzzle baffled scientists for decades, but Stephen Hawking came up with a mind-bending possible solution. Hawking theorized that black holes might not be the eternal prisons we once thought. Through the process of Hawking radiation, they slowly evaporate over an unimaginably long time, emitting particles back out into space. He initially thought this radiation was random, meaning the information was still lost. However, he later revised his theory, suggesting that the information might actually escape, encoded in the outgoing radiation in a scrambled, almost unrecognizable form. So, if someone could collect every single particle emitted by the black hole as it died, they could theoretically reconstruct everything that ever fell in, including you. This idea leads to an even wilder possibility. Hawking, along with other physicists, explored the idea of alternative universes. He proposed that when you reach the event horizon, reality might split. In one universe, you fall into the black hole and meet your end at the singularity, as we've discussed. But in another, a different reality, the black hole might not have even existed in that timeline. You would simply continue your journey, alive and well but trapped in a different universe, with no way to ever return to ours. So what would really happen if you fell into a black hole? The honest answer is we don't know for sure. Relativity, quantum mechanics, they break down at the singularity. They give us nonsensical answers like infinite density. This tells us that our theories are incomplete. We need a new theory, a theory of quantum gravity, to truly understand what happens in the heart of a black hole. Is it a gateway to another universe? Is it a place where information is stored and later released? Or is it simply the ultimate endpoint? These questions remain some of the greatest challenges in science, reminding us that the universe is far more mysterious and wonderful than we can yet imagine.